talk about this. We talked about the first and the second. So give me an abbreviation or a shortened version of what's Newton's first law say. No, his first law.
An
Object at rest will stay in rest. That's called the law of inertia. Good. Newton's second law doesn't have as catchy of a phrase here, but Newton's second law is the net force equation. So F net equals ma, right? That's the equation for Newton's second law. His third law has another equally popular tagline, right? An equal and opposite reaction. For every action, there is an equal and opposite reaction. That's true, right? For every force that's acting on object B is then exerting an equal force in the opposite direction on object A. Okay, so we talked about this a little bit with what we call the normal force. If my cup's resting on the table, gravity's pulling it downward and it's exerting a force on the table, but it's not falling through the table, is it? Right? It's not falling. The table is exerting an equal force back up on that object. And so that's considered Newton's third law. Okay, so for every action, there is an equal and opposite reaction. For every force, there's an equal and opposite force, okay? We did go through this table of types of forces, so I don't know if there's any questions about that, but we'll keep kind of moving here if there's not, all right?
My pencil's way too.
All right, the first main, not first, but what we're going to talk about today is called the normal force, okay? And do you remember what the normal force is? I drew it the other day. I explained it just a little bit. It does go up and down, but what's it always stemming from? Perpendicular to the surface, right? The normal force is exerted by the surface, okay? Normal force is exerted anytime it's something on a surface, okay? And so for an object that's resting on a table, the gravitational force is pulling it down, and the table exerts a normal force back up on it. When that happens, and when my object is at rest, my net force is equal to 0. We talked about that a little bit previously, right? There are two scenarios in which my net force is equal to 0. At rest is one of them. Do you remember what the other one is? Constant velocity or constant speed, right? Those are the two instances in which my net force is 0, because F net equals mass times acceleration. So if my acceleration is 0, my net force would have to be 0 as well. Three different examples of an object, and we're going to calculate these values for normal force, okay? I don't love necessarily the diagrams they drew because I like for the forces to be stemming from something, so I'm going to draw over the diagram a little bit, and if you want to draw these to the side or something, we can, but do you remember what it's called, what a force diagram is called? A free body diagram. Okay, so here's my object. I represent it with a dot, right? And the force that goes downward is the force due to gravity, right? Fg. The force that's being exerted upward is the normal force, okay? Do I know anything about these forces in this scenario? Do I know, are they going to be equal or not equal? They're going to be equal, right? Because are there any other forces that are acting on that object? No, and it is at rest. Okay, so I want to start the system of how we start solving force problems, okay? When we solve a force problem, we set up a net force equation. And we say the net force of a system is any positive forces, normal, minus any downward forces, which in this case is the gravitational force. Okay, so we've got two different scenarios as to how we can solve for the net force. We can take m times a, or we can take positive forces minus negative forces, because net means the overall or the sum. So when we do our net force equation like this, we take our positive forces minus our negative forces. Okay? Sorry, do you have a question? Minus any forces that are negative. So here's where we take into account the negative for 9.8, right? Because it's going downward. So I'm not going to do minus negative 9.8, right?
How is that the sum of all of them if it's subtracted?
So we're going to take everything that's positive minus the negatives, minus the things that are going downward, right? They're still going to have a positive value.
Plus the negatives?
Okay, if you want to think about it that way, that's fine. Right? But what's happening here? I'll show you the math, okay? Fg, we take mass times gravity. Okay, I'm sorry. Mass times 9.8. So I'm not plugging in negative 9.8 there. This value will come out positive. The only negative right there is just telling me it's going in the downward direction. Okay, so I'm always going to do positive forces minus any forces that are going downward.
And that won't always equal 0?
No, it won't always equal 0. We'll show a couple examples of what that looks like here in a second. Okay, in this case, it does equal 0 because my box is at rest. So if this box, and I don't know if I put the mass of the box anywhere. Let's just say that the box has a mass of 10 kilograms for our practice here. Okay. Is my box moving in the vertical direction at all? No. So I know my net force has to be 0, which then again mathematically proves to me that my normal force and my gravitational force are going to be equal, right? Because if I subtract over that gravitational force, it will say Fg equals Fn, right? And so that value is going to be the same. So if I wanted to solve for that, I would say 0 equals the normal force minus the mass times 9.8, right? So I would say 0 equals net normal force minus 98. I would add that to the other side, and I would say normal force equals 98 newtons. Do you see how that works, right? We knew just from the image that they were congruent. So I could have just solved for Fg and then said normal force is equal to that. I agree. Okay, but this process of writing out the net force equation is going to be something that we'll need to get used to. Okay, writing out our positives minus our negatives. Okay, so let's look at how that compares to the second problem now. All right, the second problem, there is an upward force being applied. Okay, so they're not applying enough upward force to actually lift the box off the table. It's like they're trying to lift it off the table. Do you see what's happening there? Right, they're applying an upward force, but they're not getting it off the table yet. So we've got, I'm going to redraw our forces here. We've got gravity that's pulling us down, Fg. We've got some applied force, that's 40 newtons, and I'm just going to keep that there. And then we've got the normal force as well, right? I'm just going to call this one force applied. Okay, we still have a normal force because it's still on the surface. Do we see that? We don't lose the normal force until our object comes off the surface. Okay, so as long as our object is still on the surface, I'm going to have a normal force. Would you anticipate that the normal force here is the same as it was in scenario 1, or will it be less than or greater than?
The same.
No, it's not, because here I'm taking some pressure off of that, right? I'm lifting this up. So I'm like working with the normal force here. You know what I'm saying? My applied force here is taking some of the pressure off of that normal force, and it's not having to do as much. Okay, so let's see how mathematically it works out, okay? If I set up my net force equation, I've got 2 upward forces this time. F applied or F pull or whatever you want to call it, plus the normal force minus the gravitational force. Do you see how I've got 2 upward? Those are being added together because they're vertical. I'm sorry, they're positive. And then I'm subtracting out my gravitational force because it's going negative. Would we agree with that so far? Yes or no? No, you're not seeing that?
Why is Fn minus Fg still not equal to 0?
This whole system will be equal to 0. But here I've got a third force that's taken into account. So now all 3 of those combined have to be equal to 0. Because I've got 3 forces that I have to take into account. My normal force and my gravitational force in this case are not congruent. They are not equal. Okay, so let's look at the math here. Is my object accelerating in the vertical direction? Or is it at rest? Is my object essentially at rest? Okay, so that means my net force would be 0. My applied force, we said, is 40. I don't know my normal force. That's what I'm solving for. And my Fg, I calculated over here. 9.8 times 10 is 98 newtons.
How is it at rest?
Because I'm just trying to move it, but it's not moving. Right? My box is still at rest. What?
But there's pressure taken off?
Like I'm pulling upward. Right? It would be like me trying to do this with my table. Right? I'm lifting it up, but it's not doing anything, right? I'm still applying a force. I'm relieving some of the pressure that the normal force has to do, right? Here, table, normal force. But when I start to lift it, the floor doesn't have to work as hard, right? Because I'm doing some of the work for it. Do you see the difference there? If I were going to push down on it, the normal force has to work harder. You know what I'm saying? Yeah, I don't want my heel to break. Okay. That's not hitting home for you yet?
No, I don't understand how it's still at rest. If you're taking off pressure.
Yeah, but is the box moving?
No.
No, so it's at rest. Right? The system itself, right? The box itself is not accelerating. It is in place. So that's why my net force is 0. So now all I have to do is do the math here. So 40 minus 98 gives me negative 58. 0 equals normal force minus 58, which means in this scenario, my normal force equals 58 newtons, right? Which is less than it was in our first scenario. And so that should make sense, right? As I'm lifting up on that object, I'm relieving how much work the normal force has to do. Ow. Okay, I'm relieving how much work that it has to do, right? It's got to counteract gravity, but now I'm helping it. All right, in the third scenario here, now I'm pushing down on the object. So I would expect this case, my normal force to be higher than it was before because I'm basically working with gravity now, right? I'm making it go downward more. So let's look at this last one. I'm going to redraw my forces because I just don't like the way they drew it on this diagram. So ignore those. Okay, I've got gravity. I've got my applied force in the downward direction. And then I've got the normal force. Okay, I know that purple's kind of hard to see. I don't really know what color will be easy to see. I don't know if the green is any better. Not so much. Okay. So as I set up my net force equation, I would say F net equals my upward forces, which is normal, minus both of my downward forces. So minus gravity minus my applied. Okay, because the only force that's going upward is the normal. The only ones that are going downward are gravity and the applied force. Okay, so that means my net force again is 0 because my object's at rest. Normal force is what I'm solving for. 98 and 40. So that means my normal force is equal to 138 newtons. Right? In that case, when I push down on the object, the normal force has to work harder. Right? It has to do more because more things are coming against it, right? There is an equal and opposite reaction. Okay? Tell me what questions do we have with that? Okay. Let's try a practice one here. All right, if I'm raising a 5 kilogram bucket and the rope I'm raising it with can withstand 50 newtons of tension, what is the maximum acceleration in which I can raise the bucket? Okay, do you know what I'm saying here? What happens if you're like casting a line and you reel in a really heavy fish and you go this too fast? The line snaps, right? That has to do with this exact scenario. If I pull it in slow, if I drag it in slow, it'll be fine. But if I go too fast, if I try to accelerate that object too fast, it's going to break because I can't withstand. I'm putting too much tension on that rope. Okay, so let's draw a little diagram here of this scenario. I've got a bucket that's got a tension, right? It's got a tension force going upward, right? Because my rope's going up. What's pulling downward on the bucket always? Gravity. Okay. Now, it says I'm raising a 5 kilogram bucket and the rope can withstand 50 newtons of tension. What's the maximum acceleration I can use to raise the bucket? So here's my free body diagram. That's it. No other forces are acting on it. Just my tension and my gravity. So I'm going to write out my net force equation. F net equals tension minus gravity. Right? Positive forces minus negative forces. Is the green okay? Can you see that okay? Or is that kind of tough? You need a different color?
So FG is gravity, but it's also weight.
It's weight, right? It's the force due to gravity. So it's M times G is what FG is equal to. So we're going to substitute that in here in just a second.
Why do you not have to have the normal flow?
So this is, the bucket's not on a surface, right? It's in the air. It's hanging, right? So it's being, yeah, it's not on a surface. If there was on a surface, we would have to include that. If it's on a surface of some kind. The ground still counts, right? But it's on any sort of surface. All right, so let's look at this. I am solving for acceleration. I'm solving for acceleration. So we have to do a lot of substitution in these problems. What's the other way that I can solve for the net force? F net equals ma. So I'm going to substitute this in right here. Instead of F net, I'm going to write it as mass times acceleration equals the tension force minus, what can I substitute in for Fg? What's the equation for Fg? Mass times gravity, or mass times 9.8. So I'm going to substitute those values in there. Do you see all I'm doing here is substituting these equations down here. Okay, that happens a lot. We've got to end up using multiple kind of ways to get there. We've got some numbers that we can put in now. So we've got a mass equal to 5 times the acceleration. The tension that we can have is 50 mass times 9.8, right? Little g is always equal to 9.8. Okay, so there is our negative right there that goes with our 9.8. So I'm going to go ahead and do the math here. 9.8 times 5 gives me 49. So 50. Okay. So that means my acceleration is equal to 0.2 meters per second squared. That's pretty slow, right?